RISKADAPT is a project that spans 36 months. It started on January 2023 and will conclude at the end of December 2025. To meet our aim, RISA, as the coordinator, collaborates with 17 partners from 9 countries. The consortium consists of meteorologists, climatologists, hydraulic and fluid dynamic experts, hydrologists, namely FMI, Hong Kong University, Civil and Geodetic Department of University of Ljubljana, that provide climate change forcing on structures. The consortium also includes civil engineers from Technique, University of Birmingham, and ERA that perform structural analysis, and University of Stuttgart that performs LCA-LCC analysis. Moreover, RISA, the coordinator, as an IT company, integrates all of the above in the context of a platform for risk-based adaptation decisions, where risk analysis are performed by RINA consultants with the help of social scientists from University of Utrecht and University of Groningen. The aim of RISKADAPT is very clear: to develop a modular, interoperable, and user-friendly platform that supports systemic risk-based decisions. By focusing on the asset level, we ensure that climate adaptation strategies are both targeted and effective. Let's try to break down the key objectives. RISKADAPT will be the first of its kind to integrate multiple dimensions. When we say multiple dimensions, we mean structural, social, economic, and environmental considerations into one platform. That platform is designed to be expandable, meaning it can accommodate a range of hazards and assets. RISKADAPT can be tailored to a broad spectrum of stakeholders, from asset owners and operators to engineers, local authorities, policymakers, and even insurance companies. One of the primary goals is to mitigate the risk of structural disasters, especially for critical infrastructures in response to extreme weather events. RISKADAPT enhances decision-making processes by providing risk-informed insights. Through this, decision makers will be empowered to choose the most viable and sustainable climate adaptation strategies. Let's now have a look at the pilots that will be demonstrated through the RISKADAPT. Pilot 1 is Polyphytos Road Bridge in Greece, which connects Kozani and Athens. The bridge was selected due to excessive vertical deflections, with tendon losses being a primary indicator. Pilot 2 refers to energy transmission grids in Finland. The transmission line has experienced tower failures due to high winds and snow loads, making it a valid site for testing structural resilience against these hazards. Pilot 3 is Katinara Hospital building in Trieste, which faces high winds, with past wind speeds reaching up to 150 kilometers per hour. Corrosion and concrete deterioration also plays a role. Pilot 4 is Hong Kong high-rise building. This structure has experienced multiple incidents of glass window damage, largely due to high winds and typhoon-driven rain. This slide outlines the data and processes involved in the RISKADAPT platform. First of all, we use climatological and meteorological data to assess how environmental factors like wind, ice, and rain affects assets, both now but also with future projections. We also integrate hydrological and hydraulic models to analyze water-related risks. Each asset is modeled using BIM, representing its physical and functional characteristics. Also, information concerning the materials of its asset and adaptation options is collected, including properties and degradation profiles. The platform also allows for the exploration and addition of the material degradation data, showing how structural integrity deteriorates under climate stressors. Once degradation data is input, the user can perform an asset risk assessment using a probabilistic approach to calculate the likelihood of failure over time. Each adaptation option is evaluated through an LC-LCC, while the engineering impacts of failure are provided as an output to the user. Finally, all these data are fed into a comprehensive evaluation of total risk and social impacts to support robust decision-making. At the moment, we are in the development stage of the RISKADAPT platform, and one of the main challenges we are facing is managing the different roles and access rights for the various end users across the platform functionalities. By allowing inputs from various sources, such as climatologists, engineers, sociologists, and more, the RISKADAPT platform ensures a cross-disciplinary approach that strengthens infrastructure against future risk. This seamless integration of data from climatological trends to engineering impact assessment provides a more holistic solution, making the platform a valuable tool for ensuring infrastructure resilience. As we move forward with the RISKADAPT platform, it's important to emphasize the significant impacts this tool can have once fully developed. The integration of diverse expertise and data will directly contribute to enhanced climate resilience, allowing us to better prepare for and respond to environmental changes. This is achieved through multidimensional risk assessments, structural, social, economic, and environmental considerations, which provide a clear, evidence-based approach to understanding potential vulnerabilities and planning mitigation strategies. Additionally, by facilitating collaboration across sectors, RISKADAPT will enable effective risk mitigation efforts. The platform's ability to bring together insights from engineers, urban planners, government agencies means that the decision makers will be equipped with the information they need to take timely and informed actions. This leads to enhanced decision-making for adaptation, which is crucial in a world where climate conditions are rapidly evolving. Lastly, the impacts go beyond just infrastructure resilience. The platform has the potential to generate significant economic, technological, but also societal benefits by reducing risk and enhancing infrastructure performance. RISKADAPT will help cities and regions save costs, drive innovation, and protect communities from the worst effects of climate change. In essence, RISKADAPT is not just about technology, it's about creating a system that fosters more resilient infrastructure management that can adapt to future challenges. Thank you.
We will proceed with the presentation of the ongoing work in RISKADAPT project. And since in all projects that we described, the main topic is the climate. All the analysis have as core very accurate climate data. This is a very important aspect in order to estimate the risk accurately. So the next presentation will be delivered by Marco Laine from FMI. He's in Helsinki, and it will be on climate data and climate change. And I think that, Marco, you can do it. You can share your screen.
Okay, yes. Yes.
Okay, we can
Yeah.
see your screen.
Okay, good. Hello, everybody. Also, I'm Marko Laine from Finnish Meteorological Institute. And I will have a quite practical description of the work we have done in the RISKADAPT project related to climate data and in connection with four pilot projects of RISKADAPT. You already saw those, but I recall we have the pilot one for Polyphytos road bridge. And I list here the climate forcing relevant in each case. In road bridge case, it's mainly if we think about the future climate, the changes in precipitation, which will affect the river charges there. Pilot 2 deals with the energy transmission grid in the Nordic climate, and the pilot case is one power line in eastern Finland affected mainly by icing and snow load. Pilot 3 is the Katinara Hospital in Trieste, which is affected by the strong Bora winds. And in addition, we have pilot 4 in Hong Kong, where the tall glass facade buildings are affected by heavy wind and rain. We are here mainly dealing with climate extremes, extreme weather, and extremes in the sense that what we can expect in the future compared to the future climate. And what we have done at FMI for this project is extreme value analysis using statistical tools to estimate the probabilities of different events and compare the current climate and possible future scenarios. And we have been doing quite kind of classical extreme value analysis, calculating different return periods of events, given the historical data on the other hand, and then on the other hand, the climate simulations. A couple of things that we need to account, even if we are dealing with present climate, because in some cases the climate is changing very rapidly. The right-hand side figure, the historical maximum monthly temperature at Trieste at the location of the Katinara Hospital, and already we see a quite heavy trend there. So in doing statistical analysis, we need to account also these trends. So there's not just one current climate, but there's this current climate that is changing. So, well, I put a couple of equations here because we are doing quite standard generalized extreme value analysis. If you are familiar with this is you know what I'm talking about here. If you are not, I will not go to details, but in principle we are fitting this gave distribution, the extreme value events. It directly gives you the tail probabilities. But if we need to account, for example, trend or in statistical sense, non-stationarity of the processes, in addition to doing kind of basic gap analysis, we need to account the changes in the parameters. And also because we still have a limited amount of data for each locations, we need to account different uncertainties, even if we are dealing with the current climate. And we have been doing Bayesian statistical analysis using MCMC methods. We'll be using the standard statistical language and Python, which will give then instead of point estimates, we give uncertainty quantification for the return levels, for example. So for the current climate, we use ERA5 reanalysis and ERA5 land data, which is the best source of when we want to study the climate, of the current climate and historical climate. It's a product of European Center of Medium Range Weather Forecast, so it's based on their weather model, where they have assimilated lots of data, observational data sources. So it's given in about 30 kilometer resolution, 0.25 degree, and so it's available globally and temporarily from 1940, and it's updated constantly. So it gives, you can use it to have snapshot of the past weather and also do, for example, extreme value analysis. And the right-hand side figure shows just an example of August temperature maximum with return period of 20 years on 4 locations. And why it has not just one value, but a histogram. So the histogram accounts for the uncertainty. So even if we have several years of historical data, we still have uncertainties on these return levels. So in principle, ERA5 or ERA5 land data gives us quite comprehensive status of the current and historical climate, but then things get more complicated when we are dealing with possible futures. So, well, you know very well that these projections are based on climate models, which are numerical descriptions of the climate system and all its components, and they are a valuable tool on kind of evaluating the possible pathways to the future climate. And as we already see, typically they are based on these different greenhouse gas concentration pathways, typically CO2 concentration pathways, and also to some socio-economical pathways that will lead to those emission pathways. And we can use different scenarios to do the projections, and these projections then help us to assess the risk and impacts of climate change. RISKADAPT project, we use data available from Climate Data Store, which was mentioned, but I didn't say it aloud on ERA5 slide. We have mainly used model intercomparison projects that are CMIP6 and Eurocortex data, which both have several versions of models run for historical eras and for future with different pathways. Well, but in addition, so CMIP6 is global, so the resolution is quite coarse, even 1 degree, so like 100 kilometers, and Eurocortex is like 11 kilometers spatial resolution. But for Faroe Scandinavia, we have used so-called Harmony climate model, which is in 3.5 kilometer. so much better kilometer, so it can resolve much more processes in local scale than these other models. Still, well, just to recall challenges related to sources of uncertainties in future climate, there are things that, well, we cannot control, like volcanic activity. Some things that we could in principle control, maybe not in practice, like land use and human activities, which will affect the climate. The physics of climate is very well known, but still there are challenges. For example, the effect of aerosols is something that is usually thought of the kind of biggest uncertainty related to, for example, temperature rises. But the climate models are evolving constantly, and different processes are included. Usually we talk about global change, so like 2-degree global warming. But even for temperature, it will affect different regions differently. Typically, the northern latitudes are warming much more rapidly, and the central latitudes, and there are differences in different regions. This is from IPCC report. In RISKADAPT, one concern is the changes in precipitation, which are much harder to model, because typically the model doesn't resolve the precipitation directly, but it has to be inferred from the other variables in the model. And here's a similar figure from IPCC report that shows that, for example, in Mediterranean regions, it's projected that the precipitation will be smaller than on the global average sense. Okay, then I have a couple of slides on those pilots. So pilot one was this Polytutos road bridge. The main work here is done by University of Ljubljana. They are doing hydrological and hydrodynamical modeling on the estimated changes based on estimation of precipitation chain. On the upper right-hand corner, there's the area of the Haliakmon River basin, and overlaid is one example of Eurocordex model runs, so you can get the idea of the resolution of Eurocordex model and the precipitation. Well, I don't remember, was that just one snapshot or some average, but anyway, this was to illustrate the area and the resolution of the model. So what we have done using the Eurocordex model is to calculate this intensity, duration, frequency analysis of precipitation events using different models in the Eurocordex dataset and compare them to idea that we have of the kind of current weather. It's the dotted line in this IDF plots on the bottom. So the KeyBex data is analysis of the situation taking account of in the current weather, and there are two versions of the models, and we see that the one Eurocordex model underestimates the current situation and probably also the future prediction, and other overestimates both the current situation. So there are challenges if we want to do very local analysis on precipitation. So pilot 2 is for icing, the ice formation. The figure here is FMI research station in Finnish Lapland. So nicely shows that icing and snow load can be very big problem in northern latitudes. So here the structural risk analysis on power lines is done by ERA. One effect on icing on power transmission line is the corona losses, the loss of the electric transport, the power transportation. Not directly related to RISKADAPT project, but very interested effect of icing in Finland is its effect on wind power production, because the formation of ice on the rotor blades affects the forecast of wind power production. So this is something we are very interested also at FMI. And here we have used this 3.5 kilometer high resolution convection permitted climate model on 3 eras, historical, kind of mid 21st century and end of 21st century. Here we, because this is a very heavy model, we have only used RCP 8.5 here, and this like Eurocortex, this is original model, so we need to have some global model as a boundaries, and we have used two different boundary models. And just a snapshot on results. We have calculated icing of future climate on this domain of harmonic link that is shown on the map. And get nice results, and on the right hand side we compare the projections and historical data on combined wind speed and icing events. I don't go to details in the results, but they will be delivered within the project. Lastly, Katinara Hospital in Trieste, there the small scale modeling is done by University of Bologna, so in meter scale on building level, but FMI is providing climate data. Here we try to study the wind distribution using Eurocortex and ERA5, but here it seems that, for example, the heavy Pora wind is not very well resolved with either of those models. So we have some challenges here. This kind of spaghetti lines here give all the different Eurocortex runs on historical years and on the right on future years, and they don't give much changes in the wind distributions. But on the other hand, the backline here is the ERA5, so all these Eurocortex models overestimate the wind speed. Okay, some challenges, but that's what we have done, and that was all. Lastly, RISKADAPT will arrange session at EGU this spring. The main organizer is University of Bologna, so there will be this impact of climate change issues, extreme event, risk assessment, and damage modeling for infrastructure and assets. So you are all welcome to join, to listen us and send abstracts to this session. So thank you.